Hi, Dave Sparks, I guess is what he said. I'm with the Android media team. I've been with Android for almost 2 years now, starting with in October 2007. So today's topic is about the media framework. I basically came in to work on the framework, and so I'm going to try to give you a quick talk. This original talk was an hour. Try to cut it down to a half an hour and see how it goes. So quickly, we're going to go over the framework itself, kind of a really deep dive into what the framework looks like, some of the security things that we've thought through in the framework to prevent security issues, some of the features of Android 1.5, which came out in what we call Cupcake, and then if we have time, we'll go over some common problems that people have when they're dealing with media framework. So talking about the architecture, some of the goals that we had when we started designing the media architecture was to simplify application development. We wanted to make it really simple to write an application that produced sound or played video or whatever. So we provided a really simple interface to be able to do those things. The other thing is on these embedded systems, you have very limited resources, as I'm sure you're all aware of. And so we wanted to have a way to share all the resources in a common and have them managed by a single process. The other piece of that's really difficult is if you're writing efficient codecs, it's very difficult to make them free of any security bugs. So we're going to have a strong security model that prevented exploits through the media framework. And obviously we wanted to be able to have expansion for future growth. So when you look at the framework, at the very top of the stack is the application. And then we have a separate process called the media server that actually does all of the media applications. So that dashed line in the middle is a process boundary between the application itself and the media server process. The media server, when it generates its audio and video, is going to generate it through one of the two services that provide audio video services, Audio Flinger, which basically is a mixing engine that takes multiple streams of audio, mixes it to an output. It could be Bluetooth, it could be the speaker, a wired headset, whatever. And then the Surface Flinger, which is the 2D composition engine for Android. That takes all of the windows and composites them down to a single 2D frame buffer that is an output to the hardware. So when you look at the stack for a typical media call, at the very top of the stack is the Java application. And it's creating an object which is a proxy for an object that's actually in the media server process. So if you've looked at the Android stack, when you create a media player object in Java, it's actually a proxy for native resources that are living in a separate process called the media server. So the very top of the stack is a Java proxy object. It could be a media player, it could be a media recorder, it could be a camera object. There are a number of different ways that we abstract things. That then goes through a thin layer of Java native interface, which basically just takes it down to the native proxy. The native proxy layer, if you've looked at the code stack, we have things called like mediaplayer.cpp, mediarecorder.cpp. These are the native objects that represent the client side of the media server process. So the reason for doing that is that in the future we want to be able to allow development of native applications that take advantage of the media server process. So by having most of the code live in native code as opposed to in Java, when we allow people to do development of native applications, which we've just started doing with the recent release of the native SDK, you'll actually in the future be able to use these features from native code. And the nice thing about it is that the interface is going to be the same. So if you started writing an application, for example, in Java, and decided later on that you needed to move it to C code, the C interface looks very, very similar to the Java interface. So it's very easy to move the code down to native code. Then this is where most people get confused when they're looking at the media player stack. I've seen a lot of questions on the forums about, how do I trace the media player, let's say prepare call, to something that actually is going through instantiating the nodes in the media player as it's generating, like the codecs and the sync nodes, the source nodes, et cetera, et cetera. This is where it gets really confusing because you have this binder proxy. So the binder is an interface between two processes, inter-process communication mechanism, or remote procedures, if you want to call it that. So what binder does is it takes a packet of data and it turns it into a packet that's moved across the inter-process communication boundary. And so we have a kernel level driver that is responsible for doing that. And you basically just serialize the data, and then the kernel driver will move it into the other process. And that process has a number of binder threads, worker threads, that are responsible for picking up these packets and processing those. So the binder object, if you're looking at the code, if you want to follow the stack trace, mediaplayer.cpp then goes to something called imediaplayer. Okay, that's better. So mediaplayer.cpp makes a call into imediaplayer.cpp, and that's where the actual binder serialization takes place. So it takes the packet of data and then through the kernel driver will move that over to the media server process. And then the worker thread on the other side picks it up and acts on it. If you look at the media player interface, there's a media player service which picks up those packets when you want to, for example, instantiate a media player. And it creates a media player binder interface that it then returns back to the application. So now the application has an interface on which it can make calls into a media player that's created inside the media server process. And so that's the binder native code. And then the actual native implementation you'll find in mediaplayer-service.cpp. So for each call in the media player interface, there's a complementary call in media player service. It would be like media player service, media player client, and that's where the actual calls end up. So looking at the media server process, media player service has a number of different things that it does. It includes the media player itself, media recorder service, and the camera service. And then underneath the media player service, what we've done, I think I mentioned earlier, we talked about expansion for the future. So the media player can actually instantiate a number of different actual types of media players depending on what kind of media you want to play. If you look in the center, we have a Vorbis player. Most of the native audio files that we use are OGG Vorbis files. And Vorbis is a perceptual codec that is reasonably efficient, and because it's also open source, it's very conducive to our application. So if the media player service sees that the file that you're trying to play is a Vorbis file, it will instantiate a Vorbis player. If it's a MIDI file, then it's actually a MIDI file player. And then if it's not one of those two, it goes to OpenCore, and OpenCore is responsible for handling all of the other types of codecs like MP3, MPEG-4, et cetera, et cetera. So once we've instantiated that, what we're actually doing is passing back a handle to the application process that it can now use to talk directly to that player. So we instantiate, let's say, an OpenCore player. The binder interface that we get back on the application side is basically going through a FDEN proxy to the OpenCore player. And for each one of those players, an implementation of this abstract interface called media player interface, and defined in the media player interface.h file. So you can create a new type of player. So for example, if you wanted to have a Fiora player, or you wanted to have a GStreamer player, you could create a new media player. You just create a concrete implementation of the media player interface for that player, and it will now be able to play files. There's a little bit of work you have to do in the top-level media player service to tell it how to determine which of the players to instantiate. So there's a little bit of logic in there that looks at the file extension or snoops a few bytes in the beginning of the header of the file to determine what player it should instantiate. In other cases, it may be looking at the URL, for example. So that's an easy way to extend it and add some new functionality. And we know the people that have added, for example, we know that people have done GStream reports and are using that in place of OpenCore or in addition to OpenCore. And so it's pretty simple to do that. For the media recorder service, it's also built on top of OpenCore, and this is where you can do audio and video recording. In the case of media recorder, you have the option in the application to either instantiate a camera directly if you're going to do a video record, or you can allow the media recorder service to create one for you. And then once that's done, you actually have a direct path from the media recorder to the camera, and I'll show you that later in another diagram. Of course, the other part of the media player or media server process is the camera service. So again, this is another case where we have scarce hardware resources that we're trying to allocate to different applications. And so the media service is actually providing a way of managing those resources, so only one application can access the camera at a time. If the camera's busy, another application tries to access it, it won't be able to create a camera object. So looking at the way a media playback section works, the application is going to create a media player through the media server. And there's a few simple things that it is going to pass across to the media server process. It passes a data source. This could be a URL, it could be a file, it could be an open file descriptor. We'll talk about that a little bit later with the security model. It passes an iSurface, which is the binder interface for the Surface Flinger surface to render the video. And then it also passes the type of audio that you want to output. And this has to do with how audio gets routed in Audio Flinger. So once you've done that, the iSurface is used to send the composited video to the Surface Flinger, and the audio type is used to route audio within the Audio Flinger. So after the session is started, the application really doesn't have to do anything else. It does you do a set data source to tell it where to get the data from. You do prepare to tell it to allocate the resources. If there's hardware codecs involved, it will instantiate a hardware codec or a software codec. And then the next thing is to do call start, and at that point, the application is no longer involved in the process. The media server will actually do the decode, do the AV sync, it will hand off the finished frames to the audio and video Surface Flinger and Audio Flinger. So it's very lightweight, and that actually makes it nice because we're going across this process boundary. We don't want to be moving a lot of data across there. And then looking at the media recorder, it's a little bit more complicated because of the camera service. So in this case, the application can create a camera. And the reason you might want to do that, for example, is if you have an application that takes both stills and video, you can create a camera object. You can have, say, one button that snaps a still image, or another button that starts a video record, and it makes it really easy for the user to switch between one or the other. So in the case of when you're passing the camera object, you actually temporarily unlock the camera, give it to the media server, and the media server does its thing with the video record process. And when it's done, it will unlock it and hand it back to the application. Again, you're passing an iSurface. In this case, instead of rendering the playback video, this is used to render the preview display for if you're doing a video record, or if you're snapping a picture and you just want to see the preview in the video. And again, there's an audio source. In this case, the audio source is for the input. Typically, that's going to be the microphone. Once you've done that, you do, it's very similar to what you do with the media player. You're going to do a prepare, start record, and then stop record. And once you've done start, the application is no longer involved in the process. The media server handles all the frames, pulling the frames from the camera, feeding them to the encoders, putting timestamps on, and making sure the audio and video is synchronized, and then outputs that to a file. So now we'll talk briefly about the security model for the media server. One of the things we've done is we've isolated all the parsers and the codecs into a separate process. So your MP3 codecs, your MP3 file parser, et cetera, all of these things are located in the media server process. Now, the reason for that is it's really hard to write a codec, for example, that's very efficient and also not subject to some sort of security exploit. But, doing all the bounds checking you need to do to make sure the stream is valid is tricky to get right. You almost never get it perfect the first time. And it induces an additional overhead when you're trying to do those bounds checks. So rather than kind of do the impossible and come out with a perfect codec, we decided the best thing to do was to take this approach we call sandboxing. So sandboxing is basically putting things that are vulnerable into a separate process and assume they're going to be compromised by some sort of security hack. And then the trick is to make sure that it's running at a privilege with minimum privileges that it needs to do what it needs to do, so that if it does get compromised, it's not going to compromise the user's data. And so doing this, we've been able to, we had an actually exploit shortly after 1.0 where a security consultant had figured out how to fuzz the MP3 player and basically break the codec. And because of that, there was no way to compromise the user's data because the user's data is not in the media server process. Another thing we get out of this is we're centralizing the hardware resource so that the applications never talk directly to hardware. They're always talking to some trusted process. We can also, through this model, enforce permissions on the camera and the audio record so that someone can't write an application that takes, let's say, takes still images or video or records audio without the user's permission. And you've downloaded something from the market, if you've written an application, there's permissions that you have to put in your manifest to be able to access either audio or video. And the user gets notified when you have an application that does that, so at least they know that your application might be taking pictures of them. The important thing for us is the disclosure. You need to understand what your application might do. As I mentioned before, the media server runs at reduced privileges. It doesn't run as root, it runs as a separate user. It doesn't have access to any of the data partition and system partition. It has to run, it basically has to get permission from another application. Media server basically has read-write access to the SD card only, but it doesn't have access to any of the files in the data partition. So if an application wants to play a data file, or play, let's say, a video file or an audio file that's in its own data partition, it actually has to open that file itself and then pass an open file descriptor. The media server can't directly access those files. So that's one way we protect it. If we allow the media server to access the data partition, then you could potentially compromise the media server and then access the user's data, but there's no way to do that here. And as I mentioned before, the media server is the only thing that has direct access to hardware, and you have to have the permission in your manifest in order to access that hardware directly through the media server. So let's talk a little bit about how potentially someone could try to compromise the media server. And I mentioned before we had this situation where the MP3 codec had a vulnerability. So let's assume that I can actually, I have a codec that has a vulnerability. And let's assume that it's actually possible to write code, write a string that injects executable code into the media server process and tricks the media server into starting to execute it. So we have a compromised media server. Because the media server is running in another process as this user with limited privileges, the only thing that it can access is the data within its own process. And because the application is running in a separate process, that means users' credit card data or passwords or anything else that might be in there is not accessible to the media server. So you may have compromised the media server, but you haven't compromised the application process data. And I think when this MP3 exploit came out, the security consultant, was published this article saying how the browser had been broken, but in fact that wasn't the case. It was not possible to use the media server exploit to get the data in the browser, and that's why the sandboxing works. So, in short, no data from the application is vulnerable unless the application explicitly gives the media server permission. In the case of they've opened a file, they've passed in a file descriptor that either has read or write access, and in that case, the media server could compromise it. But you typically aren't going to do that unless it's an audio or video file, and those typically aren't something that are all that important as far as security is concerned. So quickly, I wanted to go over the Cupcake features, and then I think we'll close it out for questions. So some of the new things that we added in Cupcake are audio track and audio record in the Java interface. So this allows applications to directly access raw audio input and raw audio output. This would allow you to do things that you couldn't do before, where you can actually stream audio. So for example, you could do an internet radio application that reads audio, an MP3 stream, decodes it, and then outputs it as just raw audio through the audio track interface. Similarly, audio record now allows you to get direct access to the microphone. In the previous 1.0, you could only get access to the files after they recorded. Now you can actually get access to a live stream from the microphone. It also allows you there's a callback mechanism that supports streaming pretty well, so it calls back to the application when it needs more data. And we also made a provision for static buffers if you wanted to create sound effects. So this allows you to basically load a sound effect into memory and then just trigger it instead of having to stream from a file or something. We also introduced the JET interactive MIDI engine. So we have a MIDI player. The JET interactive MIDI engine is well suited for games. What it does is allow you to do these synchronized MIDI files. So basically, you can queue up segments of files and have it play in sequence. It's all time-stamped. You can get data back from, or callbacks from the JET engine that's timed to things that are happening in the music. So it's really good for doing like Guitar Hero or DVR type applications where you want the user to interact with the game in some musical way. We've created an open source engine. The engine's part of the Android platform. And we've also open sourced the tools for creating the files. So all the authoring tools are now available. And there's a VST plugin if you wanted to generate and test files that way. So I think we're going to skip directly to Q&A here. Any questions?
有任何人想让我问一下这个一些问题吗？机会难得哦，来哦。
Hi David. I know some mobile phones have two cameras, right? And I traced the camera code. It seems to me camera service has the assumption that it only have one camera. So is framework going to support two cameras in the future?
Yeah, so we have plans to support two cameras in the future. We're starting to talk to several companies about video telephony, support for video telephony in the future, as well as things like G-Talk video. So definitely it's something we want to do. I don't think there's too much we need to do to support additional cameras. Essentially all you need is a way to create a camera specifying whether you want the forward-facing or rear-facing camera. That's definitely something we want to do.
还有人其他人有什么问题问吗？对吧？人从那个 Virginia 那边过来，这样机会难得哦。那如果没有其他想问的话，我们就先谢谢一下 David。